Welcome back. Let's continue with the index structures, because this is actually called an index, what we are doing. So it's an index in the index, sort of, right? So there's the standard inverted index, and now we are looking at the data structure that organize the data structures that organize the dictionary. All right, so this is clear, right? You have the version where you put the terms all over the place, and then you have the version we just put them in the leaves, and then the whatever is on the other node is only for comparison purposes, but they don't have any posting list. Now in practice, here I just put O, J, and S, like some made up things, but they compare, right? J is between B and node and so on. In practice, that's not what you do, because you would have to figure out extra terms that are not in the leaves. In practice, what you do is this. You basically reuse some of the terms that are on the leaves, you reuse them for the comparison purposes with a semantic of open-closed intervals. What do I mean here? I mean here that, for example, not everything that is strictly before is on the left, everything that is after or equal, including itself, is on the right, right? The same here, or everything before it is on the left, everything after it or itself is on the right, right? So what do you do in order to populate the nodes here? Well, you just take the leftmost of the right branch, right? So here you just pick on that side, the leftmost term is or, so you just put or. On that side, the leftmost one, there's only one, is 2, so you put 2. On that side, the leftmost one on the right side is not, and so on, right? So this is how we pick them. For every node, you put the leftmost term from the right. For whom does that make sense? Right, it's just a trick so that you don't have to invent comparison keys. You just take these ones. It's a slight difference with this. So in that case, you had the strict comparison, right? So it's strictly before, strictly after, and the equality was the node itself. But since here we are only at the leaves, then of course we have to account for equality being on the right as well, right? So this is what I put in there, right? On the left is strictly before, on the right it's strictly after or equal to the term. Okay, now this is a concrete example of some binary search tree where I put actual words. And if we look for should, for example, the same one we've been looking for earlier, we start at the root, we compare with 2, S comes before T, so we go on the left. Then we have what is that? Merely M. M is before S, so S is on the right, so you go to the right. S is before T, so you go to the left. And then you have should here, now we have found it, right? So the complexity is logarithmic of that. In fact, what we've just done here is exactly what your brain did earlier when you directly found it in the sorted list, right? It's only a materialization in space, in actual memory of what we do in our brain in time with the binary search. Okay, logarithmic. Now, what I've showed you here is all with binary trees in the sense that every node in the tree has at most 2 children, 0, 1, or 2, but at most 2 children. This is why it's called a binary tree. Now, this wouldn't be very efficient. If we just put 2 children everywhere, then for example, imagine you have 1,000 terms, then you need a depth of 10. If you have 1,000,000 terms, you need a depth of 20. Now, a depth of 20, if you have something that big, a depth of 20 is actually not very convenient. The main reason is that this doesn't all happen in memory. Of course, a depth of 20 in a binary tree, if everything is in memory, then that's fine. These are just lookups, a series of 20 lookups in O of 1 or 20 comparisons in O of 1. That's fine, right? Just follow pointers. So this is going to be quick. In practice, a lot of your index is on disk. It's not all in memory. This is the reason why we don't want to have too much depth in the tree. So we don't really stick to just having 2 children. Instead, what we do is that we allow for more children, right? So instead of having just one value here with 2 children, one is smaller, everything smaller is on the left, everything larger is on the right. Now we reason with intervals. Like for example, in that case, everything that is before J is on the left, between J and M is in the middle, and after M is on the right. So you see how that generalizes to more than 2 children, right? You just need to have more than 1 key on every node, right? How many keys? The number of children minus 1. We'll come back to this. Here you have 3 children, so you need 2 keys, 2 comparison keys. All right. Another reason, and this is also related to the depth, is that I assume you studied a bit how hardware works, like the drives, a hard drive. You know that a hard drive has latency. So if you take the old ones, the mechanical ones, you know that they are made of a rotating disk, and then you have a reading head. And then when you need to read data, you need to wait for the disk to have the data that you're looking for where the head is, right? So you have a latency, because when it rotates, every time you need to wait. Of course, it doesn't seem like a lot, because the hard drives, they turn 1,000 times per minute nowadays, right? So it rotates very fast, but you still have this latency. So what you cannot do is read the bit by bit from the hard drive. There is no way you can read bit by bit, because at every bit you will have to wait, again, for the latency. For this reason, we do not access the data on the hard drives bit by bit or even byte by byte. We access them in blocks. Of what size, roughly? The order of magnitude? On Zoom, maybe? Let me do a test. Who knows? I promise I will not ask. Who knows it? Okay. Sometimes I just want to make sure that it's not just because you're shy. Okay. Roughly, the block size when you read from disk is 4,000 bytes, 4 kilobytes, right? So you read 4 kilobytes at a time. Now, if you consider that this is going to be read from disk, for example, of all of that part right here, so let's say this here, you would ideally want that to not be smaller than a block. Because if this is, let's say this is 200 bytes, you're anyway going to read 4 kilobytes from disk. So it's a waste of resources if you only put 200 bytes in there. So you want this to be at least 4 kilobytes, maybe even multiples of that. You don't mind reading more bytes, but basically you want this to be at least thousands of bytes. For whom is that clear? Right. So this is another reason. So it has the effect that what you read from this will correspond to the block access, plus the depth of the tree will be less. Right? If you increase the number of children per node, then you have less depth in the tree. All right. Now, this is an example where I have here 2 children for the root and 4 children in here. So you see, this node right here has 1, 2, 3, 4 children. The arrow here goes through, but this is only going through. There is nothing connected there and there either, right? It's really just 1, 2, 3, 4 children. This here is called a B+ tree, right? So now I have to give you a bit of warning about B trees and B+ trees. You can try to look that up over the internet, find a Wikipedia page or find lectures that give you definitions of B trees and B+ trees. It's basically a big mess in the sense that nobody will give you the same definitions or the same parameters or and so on. So you have to basically live with that there is no real standard that everybody is doing. It's quite complex. There are different conventions. For the purpose of this course, I'm going to give you one, but you need to be aware that the conventions might be different somewhere else. But once you have learned B+ trees with a specific set of conventions, it will be super easy to adapt to other conventions after that, right? So, but just to give you some environments with specific conventions, I will give you some and so on. But you are warned that if you try to go to Wikipedia, it might not exactly match what I'm going to tell you. All right. Or even ChatGPT. Nowadays, I need to include ChatGPT and not just Wikipedia, right? All right. So, I need to remove the toolbar on the bottom. I know the trick. It's actually your predecessors who told me I need to click here, and then it disappears. So this is the trick to make the toolbar disappear. All right. So first, this I think everybody agrees with. In a B+ tree, all leaves are at the same depth. It cannot be that you have a depth on one side, let's say a depth of 3, and then the depth of 4, and so on. All leaves are at the same depth, right? So in that case, they are depth -2, so or depth 2. So if you consider this is like Erdgeschoss, this is first Untergeschoss and second Untergeschoss, right? So everything is at the same level, at the same depth. Okay, that's the first condition, the first requirement. Why? This actually makes it more efficient for disk access as well, because you really have something structured in levels like that. Second, you have another constraint that is about the number of children that every node is allowed to have. This is an interval. You have a lower limit and you have an upper limit. In that case, we have the convention that all the non-leaf nodes have between 3 and 5 children. So 3, 4, or 5. Non-leaf, why? Because the leaves, of course, don't have any children, right? So on the non-leaf nodes have between 3 and 5 children. So you can check. There's 4 here, 4 there. Nobody is objecting. The root, did you see the root? Is it what you were about to say? So the root has 2, right? Or is it what you wanted to say? Yeah, exactly. So the root has 2. And this is fine because we make an exception. The only exception that we make to this rule of the intervals is the root. The upper bound is still applying to the root, but the lower bound isn't. So the roots can have at most 5 children, but it can have less than 3, right? So we make an exception. This is why we have only 2 here, right? But everywhere else in the tree, it has to be 3, 4, or 5. Everybody's following? Okay. Now, you see that here I have different colors from the leaf for the leaves and for the non-leaves. This is the same that I showed you on the binary trees before, when I told you there's the 2 conventions. Either you spread the terms all over the place, or you just put them on the leaves, right? So here, they're only on the leaves. The actual terms and posting lists are on the leaves, and the other keys that are in gray above, they're only here for comparison purposes. Right. So this is the second convention that I showed you earlier. And by the way, if you actually look carefully, how did we put possess here? We just look on the right, the leftmost one is possess. This is why we picked this key here. That's basically less than strictly and then more or equal on the right. So this is why it's called the B plus tree. The plus in B plus tree includes the fact that the terms are only on the leaves. If you have just a B tree, then they are everywhere. So B tree, the terms are everywhere. B plus tree, they are only on the leaves, right? This is one of the differences between these. So this here is a B tree because now the terms are everywhere and not just on the leaves. So this is a B tree. This is a B plus tree. This is a B tree. And typically these intervals of children, we put them as a prefix in front of the tree. So if we say it's a 2, 4 B tree, it means that it's a B tree, so the terms are everywhere, and every node that is not a leaf has between 2 and 4 children, right? 2, 3, or 4, except the roots that can have less, but in fact, it's already 2, the minimum here, so it doesn't make any sense. Right? Why does it not make sense if the root has 1 child? Anybody? 1 child for the root? Exactly, that's the idea. So it does make sense to have only 1 child for the root because then you can just kick it out. You can just get rid of it or merge it with the node. So this is the reason why less than 2 will never happen, just because it doesn't make sense. All right. Okay, so this would be a 3, 5 B plus tree. This is a 3, 5 B plus tree. This is a 2, 4 B tree. Who agrees? Okay, everybody. So this is how it works. You have these parameters right there. Now, in B plus tree, you have the plus. So of course, plus is quite fancy for the streaming services that give you all of that. So it's the same with a B plus tree. It's a B plus subscription. So you have plenty of bells and whistles that come with it. So since you have all of the terms on the leaves, you actually have one more thing. You have these magic pointers. So what happens is that in a B plus tree, you also have these pointers there. What are they for? You can basically get a whole linked list over all of the terms in the dictionary. This allows you to efficiently traverse the whole list linearly, right? It's basically faster. If you don't have these pointers, you can still traverse, right? But then you would have to traverse like this, right? You keep going up and down and up and down. But if you directly put these additional pointers in there, then you can just do it as a single traversal very efficiently. This is part of the B plus tree. You don't have that in the B tree, right? It would be also more complex because the terms are everywhere. But in the B plus tree, since they're all on the leaves, then you can do that. Okay, now this is where the conventions might diverge. How do you parameterize these intervals? You could pick any two integers, right? But it wouldn't make sense. You still need some rules of thumb to pick the two integers for the lower bound and upper bound. So one convention, the one we take in this lecture, is that we have a parameter d, just one parameter d, and the intervals we pick are of the form d plus 1 to d plus 1. Right, d plus 1 to d plus 1. So now we can just plug 0, 1, 2. So if it's 0, then that's basically 0 plus 1, 2 times 0 plus 1. So 1 and 1, that's useless. So 1, 1 is just a corner case, like a vector space of dimension 0, right? But now let's put d equals 1. That puts us with 2 and 3. So we have 2, 3, b plus 3s. Then d equals 2. That puts us with 3 and 5, and so on, right? So this is basically what you get. Again, 1, 1 doesn't make sense. It's totally useless. This is why it starts to be useful. So 2, 3, 3, 5, 4, 7, and so on. You just plug this parameter d. This is only a convention. The only thing that really matters is that it's roughly double, right? So the second number should be roughly double the first one. Some people will have d 2d or d plus 1 2d or these variations like that. But let's take for the purpose of this course, d plus 1 2d plus 1. In practice, d is going to be larger than that, right? On my slides, I cannot put nodes with 1,000 keys because that wouldn't hold, right? But in practice, you have, of course, much bigger nodes with many more keys, right? But for my slides, I take these smaller numbers. Now, something you need to be aware of is that if I say between 3 and 5 children, what does it mean for the number of keys? Is it also between 3 and 5, or is it, what is the interval for the keys? If I can have between 3 and 5 children, yes? Let me think. I always need to think before I, 3, almost, no, it was the -1. Let me show you. So entries means n minus 1 intervals. So basically, if you have 3 keys, then you have 4 children. So if you have between 3 and 5 keys, that's between 4 and 6 children. The other way around, if you have between 3 and 5 children, then you have between 2 and 4 keys. Who agrees? Right. I keep making the same confusion in my brain. I always need to think like, is it +1, is it -1, and so on. So maybe just drawing it actually helps me a lot in any case. So between 3 and 5 children means between 2 and 4 keys. Why does it matter? Because look here. We constrain the number of children for the non-leaf nodes. But how do we constrain the size of the leaf nodes? Well, we constrain it in that way. If we have a 3, 5 b plus 3, between 3 and 5 children means we need between 2 and 4 keys on every leaf. For whom is that clear? So this rule with the interval also applies to the leaves, but with a -1, because you have one less key than intervals. Right. And again, if you hesitate +1, -1, because again, I always do the mistake. This is why I always need to think every time I say it's +1, -1. So just draw it like this, and then it's clear. That's what I do for myself. Okay. Right. So if it's d plus 1, 2d plus 1 for the children, then it means the number of keys. So the key, what we call keys, these values here. So keys are between d and 2d. All right. There is another convention that you find that not only the parameters with d plus 1, 2d plus 1 might be different, but when people say 3, 5, b plus 3, we mean in the course between 3 and 5 children. There are people who mean between 3 and 5 keys. So they parameterize the keys and not the children. So you see, it's really a bit of a mess in the conventions. So just let's take this convention right here for the course, and don't be surprised if you see other conventions at other places. For the purpose of the course, the two numbers you see as a prefix of b plus 3 is the number of children interval of the form d plus 1 to d plus 1. So if we take a 3, 5 b plus 3, I have an animation for you to show you what's going to happen. Imagine we populate it. We keep adding more and more and more and more keys. So we start with just 1, so it's the root, depth 0, just has this this single node, and we add one. So remember, we take 3, 5, b plus 3. So it means I have between 2 and 4 keys. So here I have only one, but this is fine, it's the root, right? So I don't mind that I have less than 2 values. Now I add one, I'm going to add increasing integers, right? Of course, in reality, it's not going to be increasing integers, but just for the animation. So now I put a 2, so now I have a root with 2 keys. I add 3, we're still fine. I add 4, we're still fine, right? So now we still have a very simple tree with just the roots. Now I have 4 keys, now I'm reaching the maximum. What if I add one more? Now we have a problem. We have a problem because now this is breaching the rule that there must be between 2 and 4 keys, right? Hypothetically, if there were children in there, there would be 6, right? There would be 1 here, 2, 3, 4, 5. That would be 6 children. It's above 5. So that's not fine. What do? We just split it. There you go. What key do we put here? Well, we just take the one from the right, again, the leftmost of the right side. Now there's something arbitrary in there. Right here, I did d plus 1 d. I could have done d plus 1, right? It's a matter of convention here, but let's just split it in that way. Now we have one more depth, right? Level of depth. Let's keep adding 6, 7, it's still fine. Now 8. What do? We have to split it, right? We go one level up. There you go. Still following? Right? So now we have 2 keys on the root. Now we continue, 9, 10. Now we have again to split here. Now we have 3 keys on the root. And now I fast forward. So I just directly fast forward there all the way that we make it completely full. Then I add 17 here. We have to split, but look at what's going to happen now. Now I have the problem at the root, right? So I need to split again, and this is how I get an extra level, right? So once in a while, you're going to get extra levels, and the tree is just growing deeper and deeper. All right, now let's remove things. I'm really sorry about this pop-up. I just never managed to get rid of it. I managed to get rid of it on one other machine, but I never managed to reproduce the thing to get rid of the antivirus pop-up here. So apologies for that. So we remove 12. That's fine. It has 2 keys between 2 and 4. That's fine. Now I remove here. That's still fine. Now we are no longer fine because we only have 1 key. We have to have between 2 and 4. So here there would be hypothetically 2 children if it had any children, and 2 is less than 3. So what do? We have to merge back, right? It's the opposite of the split. Now we have to merge. So let's merge it like this. But now we have the problem with 16. That is just 1, and it's not the root, so it doesn't work. Now we merge, and now we reduced the depth, right? So we are not going to implement one in the exercises because implementing a B plus tree is very, very challenging. It looks, maybe if you just look at the animation, it looks simple, but if you try to implement it, this is very, very tough to actually do. And one of the reasons is because of all these conventions, the different ways that you can actually implement a B plus tree. And then on top of that comes the challenge, I already kind of told you, right? But part of it is in memory, part of it is on disk, right, in reality. So what's going to happen? Of course, you anyway have a copy of the entire thing on disk, right? But what's going to happen in reality is that you read from disk the upper part of your index and you make a copy in memory. So that part here is going to be very fast because you're looking at lookups in the working memory, in the RAM. This is very fast. Things get slower when you go to the lower levels because now you read from disk. But what you need to see here is that we don't read everything from disk. We only read from disk the part that we're interested in. Right. And since we have organized everything, not as a binary tree, but with more keys in there, we are reading in blocks. So this is going to be efficient. This here is a B plus tree. Who followed? Okay. This is not just for information retrieval. You have exactly the same thing in relational databases, in document stores, in many, many database systems. You have exactly the same structure. So to summarize, we have hash indices and B plus tree indices. Hash indices, they do it in O of 1, constant complexity, but they do not support range queries, and it takes a lot of space. The B plus trees, they are more space efficient. They support range queries, but they take logarithmic time instead of constant complexity. So that's the idea. And I added, of course, plus posting list because we focus so much on the structure that we forgot them. But of course, you have all of the posting lists that are in there, right? Every single node on the leaf, because it's a B plus tree, so it's just the leaves, has the posting list. So now, if you look up a word, you just start here at the top, and then you just percolate. I think that's how the mathematicians call it. So it percolates down all the way to where you have the actual posting list you're looking for. Plus, it works on ranges. If I would, for example, if I want to go between possess and that, I just look up possess, I just look up that, and then I use my magic pointer. Remember the magic pointer? I have it there. Wow, that's so many slides. This magic pointer, right? Now I come back. So thanks to my magic pointer, I'm able to, now if I have these two bounds, I'm able to traverse efficiently as a single linked list, just following the pointers between my two bounds. So I can very efficiently find ranges, and then I go through all the posting lists of that range. All right, I'm done with B plus trees. This here is the index structure. So now you have a choice, either the hash index or the B plus tree index for the dictionary. The dictionary, that's the name we give to the terms on the left of the standard inverted index. A few seconds of break before we move on to a new feature of our system. Any questions? No questions? On Zoom, any questions? Okay. So let's add more features. What did we have as features right now? We have the feature of the Booleans and or not. We have the feature of the quotes. We can just write phrases and quote things. Now we saw the byword index, the positional index. Let's add the wildcard feature. The wildcard feature is a way of writing a query when you don't know all the letters, right? So you just put a star, meaning, okay, it can be anything. It's any sequence of characters, right? Not to be confused with the clean star, which is in regular expressions that would come after a repeatable character, right? Here, it's really just the star by itself in there. For example, ETH would match it, Switzerland, Zurich, mathematics, anything would just match that sequence of characters. So of course, nobody is actually searching for this. That would return the whole internet, right? So nobody does that in practice. The way you use it is by having some word, and then you leave the middle of it with a star. In that case, it would be useful because Zurich might be spelled in multiple ways. Zurich, so it can be UE, it can be umlaut, it can be an U without the umlaut in English. So maybe you want to put the query in that way to allow for multiple spellings. But of course, since we have a new feature, now we need to implement it. So how do we implement that now with our index? How do we extend what we have in order to support the wildcard queries? Oh, I even added them here. So these are, for example, examples of what it would match. Of course, it would match more than that. You can put whatever you want instead of the star, right? But in particular, the intent of whoever wrote that query was probably to catch these three. Now, another way that you can do this is to put it at the end. This is basically a simulation of stemming, right? So it's basically for the families of words. If you have informat, then you match informatics, information, informative, and so on. So that's what the star at the end could give you. And then, of course, you can have multiple wildcards. This is, of course, completely made up, right? But basically, you would match whatever you put, even nothing, right? The star can also match nothing. So this would match all of this. Another way to use it is at the beginning. So here you match economics, physics, or everything that adds that ends with X would be matched by this query. Math star would match mathematician, mathematics, mathematical. Now, question for you. Given what we have right now, we have the standard inverted index. Let's assume we even have a B plus tree, because now we know how to build one. What do you think? Can I execute efficiently the top one or the bottom one? Which one of the two is the easiest to look up given the index that we have? So I give you some time to think, then we can do a poll, unless you want to directly answer. Does somebody have the answer? Yes? Why? This is correct. So I'm repeating. So the second one is easier, math star, because we indexed from the start, the way we built the B+3, it started lexicographically. So it's from the left to the right. So indeed, you're absolutely correct. This one, the one with the wildcard at the end, this is something we get for free with the structures we already have. So let's do it. So here I made up something. Of course, in reality, it's going to be actual words in there, but I just made up just to simplify things a little bit. So imagine that now we have this query BA star, and we want to look it up. So what we need to do is we can interpret that as a range, right? This is in fact a range. This is the range BA included all the way to BB excluded. Who agrees? Right? This is what it is. So now we just treat it as a range, and we look up the two bounds of the range, so BA and BB. And now we get, so here first, we do it very coarsely. So we can eliminate everything in there. We can eliminate everything in there. And then we just are here. Then we go one level down and we fine tune. And now we are here, right? So now these are the posting lists that we are interested in, right? So again, what did I do? I looked up BA and BB. So BA, the closest I found, that was BA following it, and BB, the closest I found preceding it, that's exclusive, right? So BB is excluded, that's BAD. Now, remember that B+3s support efficiently range queries. So it means that it's very easy to go through all of these posting lists as a single traversal from the left to the right. And again, B+3 means I will have even a magic pointer between the two. So now, I just follow the postings lists and I merge them. It's a union of the postings lists, and that will return the results of my query. Who agrees with that this returns the desired results? Okay, very good. Okay, then let's do the other one now. This one, do you have a question? Yeah, sorry. So let's do the other one. Star AC, how do we do that? Well, it's not so easy because now we are the other way around, right? So now there is no easy way. It's basically all over the place in my index. But I can do something at compile time. If I anticipate that people are going to use my system in this way, then I can maybe build a different index, an additional index. How do I do that? Well, I'm going to write all of the terms backwards, and then I'm going to build the index with the backward terms, right? Then I rebuild the index with the backward terms. And then what do I look for in this index? What interval do I look for? Yes? Exactly, CA all the way to CB, right? So this is what I do. There you go. You have CA and CAB, postings lists for terms AC and BAC, and then you return that, right? What's important here is that this is not the original index. This is not the original standard inverted index. This is an additional one. So we built extra structures in order to make more queries faster. This is what happens in any relational database systems or any database system. You basically build more things at compile time before users even ask for it. This consumes space. This also consumes time in order to build the structure. But then when people use your system, you're going to be faster. It's a compromise to make. Typically, what you do in a company, you observe what your customers are doing, you observe the sort of things that they do, and then you try to optimize what is widespread, the sort of things that they do a lot. So if nobody ever does that query, you don't need to build a structure, but if you observe that a lot of your customers actually frequently input that type of query, then you will build that additional index structure with the backwards terms. So that's a reverse tree. I don't know why I put B3 in there. That's a B+3. So that's a mistake. It's a B+3 because it's at the leaves, right? I have to fix that. Okay. Now, we are almost done with today. We'll finish with the wildcard queries. Let's look at this one. It has a wildcard in the middle. So how can we query that one? Can we rewrite it differently? Like this, right? You could look for ZU star and star CH, like this. Then you look for ZU star in the B+3 and for star CH in the reverse, B+3. Then you do the union or the intersection. Who thinks the union? Who thinks the intersection? Okay, so yes, the intersection. All right. Can there be false positives? Who thinks there can be false positives? In that case, probably not, right? But in that case, can there be false positives here? Can you give me an example of false positive? Yes? Yeah. And for example, do you have a concrete example here? Yeah. Statics is a false positive. You see that statics would basically not fit the query, but if you try to rewrite the query as static star and statics, then you have a false positive with statics. False negatives? That cannot happen, right? But false positives, yes. So it needs to be, you need to be careful, right? This way, by the way, this pattern of having a query, then using indices in order to get some results with false positives, and then you do some additional work to get rid of the false positives, this is a common pattern in databases. Very, very often you do that. The index will give you too many results, but still very quickly, and then you remove some of the false positives in there. Right? So this is not just for the case of wildcards, but everywhere. So this is called post-filtering. You basically use the index and then you post-filter, but the cost of post-filtering will be much less than doing it on the entire database, right? Because you had the index that basically accelerated things for you. So in some cases, you're lucky that the index alone is enough, directly gives you the results, but in many cases, it's the index plus some post-filtering after that to give you the results. We have a few more minutes. I could start with the Permuterm index. Who wants me to show you the Permuterm index? Who wants to eat? I think there was more hands for the Permuterm index. Let me do the Permuterm index. I promise I will let you go. I will let you go on time. All right. So the Permuterm index is yet another additional index that you can build. The way it works is by inserting a dollar sign. That means the start or the end of the word, and then you rotate. It's called a rotation. Imagine that you put these letters P, L, A, and T on a circle, plus a dollar between the P and the T. Right? You put them on a circle, and then you do all the possible rotations. This is what you get. Who agrees? Right? These are just rotations. It's all the way you put it in a circle. Then you read 1, 2, 3, 4, 5, 6 characters. So these are called the rotations. And do you see now how that would help you answer this query here, PL star T? What would you look up in the Permuterm index if you have something that indexes what is in the middle? On Zoom, maybe? Somebody? What prefix should I look for in the rotations to solve the query PL star T? Yes? Yes? Can you go further than that? Simplify further? Yes, exactly. T $PL star, and you just look it up in the Permuterm index. This is the solution for the wildcards that are in the middle. For the wildcards at the beginning and end, these are the two I showed you, the normal index, the reverse index. If the wildcard is in the middle, you just rotate things all the way so that the wildcard is at the end. So the T basically went to the left, but you have the dollar that keeps track of the separation. And now you look up like this T dollar plan, and T dollar plan, of course, since you build the index, is going 2 points back 2 plans, right? Because an index always shows the opposite way, right? So that's it, how you actually solve these queries, right? So what you do is that you basically build an index by rotating every term that you have. You compute all rotations, and then you build a B+3 on the rotations that point back to the original term. So all of these points to plants. Then you do the same here, ETH and so on. You do it for all of the terms. You sort, you build your B+3, and you have, I oversimplified here, right? But basically what you have is a huge index, a huge tree that has all the rotations of all terms, but they don't point to postings list. They point to the original terms. And then when you have the original term, you can look it up in the standard inverted index, right? So here you use 2 indices, right? And this is going to be a B+3. So that's an example where I actually drew an explicit B+3, but I only put 2 words in there. I just put plant and ETH, right? But do you see now how you have a wildcard in the middle? You can now rotate all over to put the wildcard at the end, adding a $, and then you look it up as a prefix. It's a range query in there. So MPU, for example. Oh, that's another topic. So if you look for a specific wildcard, you rotate it to have the wildcard at the end, add the $, and then you resolve it as a range query on the Permuterm index. The Permuterm index will return to you the terms that match your wildcard, and then you take the terms that match your wildcard and look them up in the regular index. For whom does that make sense? All right. So I think I gave you enough material for today. And now I just will check that you followed. That looks good. Oh, everybody above 80%, and even somebody who got everything. Wonderful. Two got everything. 3. One of you below 80%. It's all right, right? You can, so there is the textbook, right? The information retrieval textbook, you can read it. You can send us emails, you can ask questions on the Element chat. By the way, if you're still not on the Element chat, let us know. Send us your ETH login, we'll make sure to add you, right? But you need to connect once to element.it.ethg.ch for us to find you. Thank you very much. Enjoy your meal and enjoy the exercise session, and see you next week at 10 a.m.